Here we have an example of the z-transform for an exponential decaying sequence given by x of n is equal to p to the power of n for n going from 0 to infinity, and meaning this is the sequence for p to the power of 0, this is 1, p to the power of 1, p to the power of 2, p to the power of 3, and so on. So this is given by this, the z-transform of this sequence here is given by this equation here. And if you remember, we had a closed form solution for this type of geometric sums. So this here is the same of p times z to the power of minus 1 and all of this to the power of n. So this is the same type of this geometric sum if we make c equals to p times z to the power of minus 1. And the solution for this type of geometric sum was given by this equation here. The thing is that now capital N goes towards infinity, so we have here the c to the power of capital N. When n goes to infinity, if the absolute value of c is smaller than 1, then this goes to 0, and then we have this solution here. So remember that we have c is equal to p to the power of z, p times z to the power of minus 1. We need that the c, absolute value of c is smaller than 1, so we need that the absolute value of p times z to the power of minus 1 is smaller than 1, and we have that the z-transform is equal to z divided by z minus p. So here we can observe that there is a fraction, and we have a 0 at the position z equals to 0, so this z, when it's equal to 0, this is a 0. And when z is equal to p, we have a pole, because when z is equal to p, so p minus p is equal to 0, so the denominator is equal to 0, and we have a pole. So if we know the pole position, we know p, and if we know p, we know the time sequence. So the location of the pole gives us very important information about the signal. But keep in mind that this solution here is only valid for all values of p which fulfill this rule that the absolute value of p times z to the power of minus 1 must be smaller than 1. So what we see is that this is true for the absolute value of c is greater than the absolute value of p. And this is also called the region of convergence. And the region of convergence is connected to the resulting stability of the system or signal. So this means that if the poles are inside the unit circle, we have a stable system. So the sum of x of n converges if the absolute value of p is smaller than 1. So in this case, we also say that the system or system is stable. So this means that we obtain a bounded output for a bounded input. This is the so-called Bible stability. So it's the bounded output for a bounded input. So in this case, we see that the resulting pole of our z-transform is inside the unit circle. So if the absolute value of p is greater than 1, then we have an exponential growth, which is basically an exploding signal or system. So this means that the output grows towards infinity, and this is an unstable signal or system. So in general, we say that a system or a signal is stable if the poles of its z-transform are inside a unit circle in the z-domain, or they are unstable if at least one pole is outside the unit circle. So these are basic properties which can be used to derive z-transforms of more complicated expressions, and they can also be used to obtain an inverse z-transform by inspection. So for instance, if we see a fraction with a pole in the z-transform, we know that the underlying time sequence has an exponential decay or oscillation in it. Observe that we can obtain a real valued decayed oscillation if we have two poles, each the conjugate complex of the other, or one with a plus capital omega and one with a minus capital omega. In this one, we cancel the imaginary part. one of the main differences compared to the discrete time Fourier transform, the DTFT. So with the Z transform, we can see if a signal or system is stable by looking at the position of the poles in the Z domain. And this is not possible for the DTFT, since there we don't know the positions of the poles. When we take a look at our downsampled signal from previous lectures and notebooks, so this was the downsampled signal. So we had our sequence multiplying with the delta impulse train. So we have this, the delta impulse train. And if we take the Z transform of all of this, so we will replace this like this here, and we will get this sum here. And we see that the effect of multiplying our signal with the delta impulse train in the Z domain is given by this expression here. So we observe that here the aliasing components appear by multiplying Z with the e to the power of minus j 2 times pi divided by capital N times k, which is in fact a shift of the frequency. So if you remember from previous lectures, the effect of the removal or reinsertion of zeros, changing the sampling rate from or into the signal x sub x squared t of n at higher sampling rate and y of m and the lower sampling rate in the Z domain is given by this equation here. So here we have the effect of the removal or insertion of zeros, changing the sampling rate from or into the signal at a higher sampling rate. And here we have a y of m at the lower sampling rate in the Z domain.